Uh, Thank you, everyone. So today I'm very happy to share some user experience about reshaping our end-to-end ML pipeline with Ray. So first, a background about my company, Motional, is we are a robotaxi company. So we can provide some limited self-driving service in Las Vegas, and we are backed by Hyundai. So I'm working in the field of ML infra. So the two top challenges we have is we are rapidly expand our driverless expansion area, which means we need to scale our ML pipeline aggressively because we need to process more data, we need to train larger models, compute more metrics, and also simulate more things. And also, we need to support continuous learning and fast iterations. So today, I will touch three phases in our end-to-end pipeline, three core phases. The first one is training data preparation before training, and the second one is the evaluation after training, and then I'll go to the training. So the first part is last mile data processing before training. So before Ray is adopted in our company, so when here is how we process data. First, we use our driverless cars to collect data in the form of daily drive log. And then here is the analogy. So it's kind of like a river. We have new data flowing every day. And then we need to first reload our data to a data warehouse. And then we need to somehow package our data. Basically, we create a few snapshots, data snapshots, and then we'll synchronize it with our in-house training platform. So it looks like just we route out the water in the river to a water factory, and then we will basically create a bottled water. And then basically then we will deliver those bottled water to a village, basically our ML engineers. So this is kind of like our legacy workflow. So you can see it requires a new data release every time. And also, it involves non-trivial operational workloads. So after we adopt Ray, what we are doing is we directly build a very high-performance pipe to route from the river directly to our village. Now the village is 10x larger because we have 10x more data requests. So instead of optimizing each step, we just rebuild this with Ray data. So the benefit first is there's no data reloading. We don't need to reload data to a warehouse, to another storage, and no synchronization to our training platform. And we can support continuous learning. And moreover, we can also, this data processing part, we have incorporated it into our optimization feedback loop along with training and eval. So I'll explain it later. So now after the Ray adoption, this is our new landscape. At upstream, we have a few data publishers. Basically, it's we have a few different data sources. You can imagine here we have different sensors like LiDAR, radar, and camera. And then we also have map data. And among all of this data, some data, they are annotated by humans. Some data, they are automatically annotated, kind of like a semi-supervised learning. So at a downstream, so this part, we built it on top of Ray. This is more like our ML code base. At the upstream, basically, is fully owned by our infra teams. But at the downstream, the green area, actually, this part, we built it on top of Ray, and it's kind of owned by our ML engineers. Specifically, this part is our training data preparation pipelines. So you can see each pipeline is kind of model specific, and you can subscribe an arbitrary number of data sources, and we can prepare features here. So you can see one important insight is as our model becomes more and more mature, actually it's more common for us to fix data bugs than not only model architecture bugs, and also we need to optimize our data besides optimizing our model. Particularly, when we use Ray, actually, it can help us to unlock some data optimization opportunities. One specific benefit is like we can use GNIs to generate some synthetic data and doing it as a data augmentation approach. But this requires a heterogeneous setup. So Ray actually is very good for this purpose. On the other hand, we can also remove some negative value or low value data. I'll explain it later in another slide. So because last mile data processing is a very classical Ray data use case, I don't want to spend too much time here, but I also want to point out like there is a caveat here. Is like you can see like when we subscribe multiple data sources, we need to do some join. But for Ray data, actually, it's not really designed for. There is no built-in join on Ray data, and especially there is no very efficient hash join. So what we can do is like a kind of a zip two data sets that have exactly the same number of rows, which is not convenient. And we tried an in-house distributed join implementation. It's scalable. We can basically, the data size we can handle can be larger than the memory data size, but there are some annoying issues like batch formats, mismatch errors. We need to manually convert our batch formats. And sometimes we also found the error info is kind of misleading. And we suspect that because of the metadata corruption. Because for sometimes we can have some workaround by just repartition the data sets, or like just write out the data set and read it back in, then it can be fixed. But anyway, I think for this part, actually there can be some potential workarounds if we really need to do large-scale join on Ray data. We can leverage some other libraries. Another point I want to bring up is like even if you just use Ray data, it may not be sufficient. Sometimes it will cause a lot of unnecessary data copies. So we need to do the optimizations in our own libraries. For example, when you do join, you can imagine like you mainly operate on the join keys, but then a lot of other fields, can be potentially large. And if you directly use the Ray data, they will just make unnecessary copies. So we need to do some optimizations here. Okay, so the next part is the model evaluation after training. So this part I think is a bit more interesting because in our AV industry, our eval actually has some unique challenges. One reason is that actually we need to compute hundreds of metrics. So when I remember that when I work in big tech companies, for example, when we optimize as ranking model or we optimize language models, those the metrics we need to evaluate, they are relatively high-level aggregated metrics like entropy or perplexity. But in our AV industry, because safety is really critical, so actually we need to evaluate metrics in many, many cases, including a lot of edge cases. So what does it mean? It means like a lot of metrics, actually we also need to do a lot of grouping. The results will be rendered as like kind of like 1D histogram or 2D heat map. So a lot of metrics. And also among these metrics, there usually can be some dependencies. So some metrics, if you computed this one first, you may need to recompute it later because there is a dependency. So it can be tricky. And another special case in our scenario is that sometimes you also prefer a heterogeneous setup. Because for some metrics, like IOU, some metric basically is like you have one object detected, and another one is your ground of truth. Then the overlap between these two objects, this kind of geometry matrix, actually, it will be much, much faster to compute them on GPUs. So how can we overcome these challenges? Before Ray adoption, so our throughput actually is quite low. For eval jobs, we just run it on a single node, although like our training runs on multiple nodes. And then if we don't carefully organize our user code, actually we will recompute our intermediate results when we compute a lot of metrics. And also, when we need to accelerate those computation, initially we use like a multiprocessing, multi-threading. But as a consequence, as a result, actually it can cause some race conditions, cause some reliability issues because this part of optimization can be kind of error prone. And another issue is like its kind of composability is not that good because you can imagine if you need to compute tons of metrics altogether, and also you need to pay attention to the dependencies, you need to group them together. So you introduce a lot of code coupling. It's kind of convoluted logic, which really makes us really hard to add new metric. And another issue is like, for example, when we use some libraries like tensor metrics, actually it's hard for us to express some more advanced metrics that involves grouping logic. So what are we gonna do here? So actually we develop an entirely new eval framework on top of array data. So there are two very important features. One is like it's ease of use. So unlike torch metrics, which presents a tensor view, actually we found like our ML engineers, they prefer tabular view. It will be easier for some ops, like especially for grouping, and also can easily support filtering, aggregation, all of this. And in our design, each metric, similar to the design of torch metrics, each metric is defined as a class, but we also have predefined dependencies within each class. Then how are we gonna use it? So for a user, it's very simple. Let's say I need to compute 100 metrics. I just specify these metrics and then run the engine, then here we go. So this is it's kind of like a declarative interface. For the engine itself, actually can hide a lot of complexities. First, by leveraging array data, we can parallelize all the metric computations. And secondly, we can handle the dependencies automatically. Basically, we know which one we need to compute first, and then we can reuse, we can kind of memorize the data, the results, and reuse it later. So we can reuse the data efficiently as well. On the other hand, we can also provide high performance. First, since we use array data, actually it can have out-of-box horizontal scaling. And moreover, we can also support like vectorization very easily. In our eval process, a lot of operators, they can be vectorized. And we can use array for built-in fault tolerance. Sometimes it's important because we have occasional out-of-memory. And also, if we want to have more speedups, such as computing IOU, we can move it to GPU to compute those metrics. So here is the improvements. For the throughput-wise, actually, we can improve by over 1,000 times. So even if we compute 20x more data, compute 10x more metrics, we can still get 10x speedup. And by using array, actually, our reliability is also much better than just doing multiprocessing, multi-threading. Another important benefit is like by using our framework, because each metric is defined as a class, so it's more like a plug-in. So it's very easy for us to add new metrics. So now this is, I think this part is more fun. This is the third part. We'll focus on the training, and we will do data curation, training, and eval together. So how are we going to do that? By using array. So first, I want to point out, like at least in our, for our jobs, data selection is super important. Because imagine like you are doing driving, a lot of time you don't really need to change your direction, you don't need to change your speed that much. So in other words, this kind of data could be very boring. So if you don't do any data selection, actually you may not be able to train very good like AV capabilities, like when you turn right, turn left, when you should slow down, when you should cut in, change lanes. And how do we do that? So one approach is we use heuristic-based offline data selection. So this is the workflow. First, we have relatively large pre-selected data. And then first we do some data denoising. We create a few filters to denoise the data. And then we will do some data mining to create different data sets. For example, what are the scenarios when you turn left? What are the scenarios turn right? When are you gonna stop at the stop sign or whatever? When you change lanes, so all of this. And then when you have all of these smaller data sets, you kind of trying to combine them into a mixed data set. And when you combine them, you need to resampling them. Some of them you want to upsampling them. Some of them you want to downsampling them. So this is how we do that. And as you can see, the main issue is like it has too many heuristics. Because when you do linting, you do denoising, the filtering is kind of a lot of heuristics. When you do data mining, the queries are a lot of heuristics. When you do sampling, you need to weight all these small data sets. It's also kind of heuristics. And another problem is that this phase, because we do it offline before training, so this phase, and I doubt that it's not this phase and the training and eval, they are kind of disconnected. Because why we believe the selected data this way is good for training a high quality model. So it's more like based on our intuition, I think. So, but what's a new approach? The new approach here is like the key insight is like I believe our eval results should guide our data curation instead of like previously it's a totally independent phase. Then how are we going to do that? What we'll do is like we can train over dynamic curated data set. So what does it mean, the dynamic? Dynamic means like every time when we have a data subset, actually it will represent the most worst learning data regarding the current model checkpoint. And after each checkpoint, actually we can refresh this data every time. So it's dynamic. It's different for each epoch. And how are we going to do that? So for here, actually we need to do some approximation for our evaluation phase because we cannot do that heavyweight evaluation. What we will do is like we replace it by a proxy to quickly measure the learnability. And how are we going to define the learnability? This is a very active research area. And here is a paper. Basically, this is just one example because for my presentation, it's more like system level optimization, not algorithm level. Just one example. This is a paper recommended by a friend, works in a data startup. So the idea is like we want to know, this is loss we computed by the current checkpoint, and then we have another holdout model, then can compute another loss, and here we compute a delta, basically trying to measure the learnability. So this is our second version. How are we going to do that? First, we prepare a holdout model for computing this metric, basically the delta here. And for this one, this is more like a frozen model. So it's a small proxy model. And then we use this one to compute, basically we call it holdout loss. So this one as a new feature column. So we store them in our input data, we can do that. And then we need to train over dynamic data set. How are we going to do that? So first, let's say we have pre-select data, still the pre-select data. Then we need to compute this kind of metric to measure the learnability. And then we select the top 10, let's say we select the top 10%. Then we get this small subset, data subset. And then we can use it to train one epoch and then produce a new model checkpoint. And then at the same time, what we can do is like we have a validation during training, basically to make sure we can fail fast if the metric does not look right. And then at the same time, we can use Ray here to kick off another job. Basically, this is a data selection job to run another data selection phase over the original data to produce a new subset. So as you can see, how are we going to do that? There is an overlap opportunity. Basically, we can overlap the data selection phase for the next epoch and the validation for the current epoch. So here we can, by using Ray, we can easily kick off two async tasks. One is data selection, one is validation. So what are simplified here? So here is a screenshot. Basically from the paper, original paper. In this paper, they claim it claims that by using this, we are able to choose low noise data, task relevant data, non-redundant data. So what does it mean here? It means like if we are able to select low noise data, then actually we don't need to do much denoising. So it means like we don't need to design very complex data linting. And it should be able to also select task relevant data. So it means like when we do, we probably don't need to do too much complex data mining to mine different scenarios to make sure it's task relevant. And we expect that it can be non-redundant. Then when we merge the data sets, actually we don't need to deduplicate the data sets. The most important one is like we hopefully the data we selected can be the most worth learning data. Then we don't really need to resample the data sets because we know these are the data we need. So here is the comparison, how we do that. First, the background is like currently, let's say if we do traditional online data selection, what are we going to do? So when we do data loading, first we will load a super batch, which is a large batch. And then by using the same metric, we can compute a top K, right? And then we can get more like local maximum because it's the maximum within that batch. And then data selection basically is part of data loading. But for our design, actually, when we compute a top K, actually we compute it over the entire data set. So what we get is a global maximum. What's the benefit here? So we expect like this could be potentially give a higher model quality because we use global maximum instead of a union of multiple local maximums. And this is actually, I believe it can be important, especially when the case of the batch size is relatively small. So maybe some people know like the difference between batch norm and group norm. Especially in vision tasks, the batch size sometimes can be very small, relatively small. And when it's small, actually batch norm may not work very well. And that's why actually their group norm is designed. So it's similar here. And another benefit is like data selection now is independent of data loading in our design, which means like we can use more data selection workers than the data loader workers. And then we can do this, we can do it faster with more resources. And it can also create overlap opportunities for us. We can overlap data selection with validation. And all of this, I really appreciate Ray, which can provide like a good elasticity. So in my opinion, so also, for example, if we want to do elastic training, actually you can use Torch Elastic. But here, I believe Ray is more generic because you can do all of this like elasticity, including the data processing around training. I think that is important. Okay, so the takeaway for me is like, that's my personal opinion. My favorite Ray features, the first one is heterogeneous computing. So this is important even when we do some data processing because you will never know if when you want to do some offload some workload to GPU. In our examples, for example, when we do data preparation, we may run some model inference on GPU to generate some synthetic data. Or sometimes when we do the eval, right, so some geometry metrics, we can move them to GPU to compute. And then another feature I really like is elastic computing. It's very easy for us to spawn an async like a job. Here is like a data selection task during training. We can do that. And this can be generically applied to data processing tasks around training. So I think this is more generic than, as I said, than Torch Elastic. However, there are some also caveats. Sometimes we need to have some workarounds for the cases not designed by Ray. So for example, like a data frame actually, I believe, is a first-class citizen in Ray data library. It's easy for vectorization because it's more like a column store. But it will make it very hard to do efficient join over large data sets, because you do, let's say, hash-based join, it's really hard to do that, so you may need to have some workarounds. Okay, I think that's all. Thank you.
All right, for Q&A.
Thank you for the talk. I just wondering, in your last slide, you mentioned the join problem, that is pretty hard to do. Have you solved this issue, joining?
Yeah, for us, we kind of bypassed the issue. Actually, our one thought is like we can leverage other libraries, because array data is very easy to convert to some other libraries like modding, like Mars, like Dask. So we can do that. But another way for us, actually, for our case, because we already have a log level parallelism, when we process our data, we have different drive logs. So within each drive log, basically we already have one level of parallelism, but within each one, we are able to do that within a single node, so it's okay. We need to just do some optimization. For example, we want to avoid like a very expensive data copies when we do join. So we do some optimizations, then we bypass this issue. But if not, if we want to do it in a scalable way, probably we'll just use some other libraries. Yeah.
Thank you for the presentation. I have a question regarding the evaluation part. So you mentioned you have lots of kind of metrics. I wonder, in the first question, do you have any abstraction on your side to define how you compute the metrics, how you aggregate the metrics? And if you have an abstraction, how you integrate that one with the array data, etc.?
For array data, so basically the data is expressed as a data frame, like kind of data frame, and then when you compute a metric, basically you parallelize it at row level, and then array data has aggregation, basically the API, right? You can do that. You can do some or something.
So your metrics definition is directly like coding against the array data API.
Yeah, how we compute it is already encoded in that class, right? So people basically, for us, the ideal case, like we can provide just a declarative interface. So people just need to specify what metric I need to compute. Then just click it, then here we go.
Cool, any other question? Yep.
Hey, thanks for the talk. May I ask, what is the rationale for choosing a PubSub system for last mile data processing system compared to just traditional ETL processing, which computes data and puts it into a data lake, and then use that for your data preparation for model training?
I think the main intuition is like we need to subscribe a few different data sources, and we join here. So first we want to separate our responsibility. The purple area basically is fully owned by our infra teams. We don't care about it as like they maintain the data sources. And the second part, this is our ML code base. So Ray is like 100% Pythonic, so it's really good for that. At the upstream, it's more like we probably use Spark doing traditional ETL jobs. So we want to decouple in this first. Yeah, I think that's main. And for this part, actually, it's not really that time sensitive. It's like because when we release data, it's like a daily, so it's not that time sensitive. So it's okay, even if you don't use that, I would say. I think decoupling is the key here.